The operational amplifier, or op-amp, is a very important chip in analog electronics. It's designed to do math. Of course, we've already used it once as a comparator. Now let's go and use it for its intended use. We've got three different op-amps in the kit. We have the TL974, we have the TLV272, and the LM741. So all of these are op-amps, but they each have a couple different variations. The 974 is a quad op-amp, meaning that there are 4 op-amps on the chip. The 272 is a dual, so one chip that has 8 pins has 2 op-amps on it, and the 741 is a single, so one 8-pin chip has 1 op-amp on it. Now let's not go into, other than the fact that one has 4, 2, and 1 op-amps on the chip, how else they vary from each other. Let's talk about the ideal op-amp. Schematically, we draw the op-amp as a triangle, and the triangle has 2 input pins, the non-inverting pin, or plus pin, and the inverting pin, the minus pin, and then it has an output pin. I'll call it V out. It also has 2 power pins. Let's call the top one VCC plus and the bottom one VCC minus. A lot of times you'll see in the future when we draw these op-amp configurations, we'll leave out VCC plus and minus. Those pins are powering the chip, and if they're not connected, the chip doesn't work. So we'll just assume that if you see a triangle drawn, those are definitely connected because it doesn't work without it. A lot of times we have, say, plus 5 volts and minus 5 volts as our power supply. Sometimes we'll use ground, but almost always it'll be minus 5. And that way the output can swing or output from plus 5 to minus 5. So V out is capable of making VCC plus and VCC minus in an ideal op-amp. We'll see later for these specific op-amps, sometimes it's not possible to do that. So we've got the non-inverting input V plus and the inverting input V minus. So somehow the op-amp's doing something on the inside to do like some kind of math involving V plus and V minus and going to V out. So what is that math? V out is going to be equal to what we call the open loop gain, or big capital G, times V plus minus V minus. And ideally, the open loop gain, or capital G, is infinity. So if V plus is 1 volt and V minus is 0 volts, then this is 1 volt. 1 volt times infinity would be V out. Of course, V out is limited to plus and minus 5, so going off towards positive infinity means that if V plus is even a little bit bigger than V minus, the output should be positive 5 volts. And if V minus is any bit bigger in magnitude than V minus bigger than V plus, then V out would be minus 5 volts. So in that mode, this would be the comparator mode, where it's basically just comparing those 2 input voltages, and whichever one is bigger, it either outputs a positive voltage or a negative voltage. That's useful in some situations, but it's not very good at doing math in particular, and I told you that this was a math chip. So let's see what happens when we add negative feedback. You're probably familiar with positive feedback. Positive feedback, if I took my mic and put it near the speaker, the speaker would make a loud noise into the mic would amplify that and make the speaker louder, which would then make the microphone see a bigger signal, and it would spiral upwards and upwards until it got as loud as it could. We don't want that. We want negative feedback, and negative feedback means that the output tends to reduce the magnitude of the output instead of increasing it. So here's a circuit with negative feedback. We take the output voltage, we put it through some kind of circuit. In this case, I'll draw a voltage divider. And we'll feed it back to the negative or inverting pin of the input. And so now I've got a circuit with a input voltage and an output voltage. And we'll have a series of different configurations for these op-amps that have negative feedback. Usually, 2 resistors, maybe a capacitor, some stuff in there. Usually 1 input and 1 output. and an equation that says V out is going to be a function of V in, and I don't know, I'll call this R1 and R2, and it'll be a function of R1, and it'll be a function of R2, and all the other components. Now, we're going to explicitly solve these in the future. Let's not do that just yet. Let's just do a thought experiment of what happens here. Let's say that initially, let's say we're powered with plus or minus 5. Okay, so that's how we know the swing that V out will take. Let's say that V out is initially, I don't know, 0 volts, because we're just going to assume that nothing was going on, so it was just outputting 0. And let's say that V in becomes 1 volt. Maybe it's coming from a phototransistor or a potentiometer, some kind of input signal. So what does this equation, the main equation for our op-amp, say? Well, when 1 volt is bigger than whatever this voltage is, this should become more positive. So when this voltage is 0, we have a voltage divider. The voltage divider always makes a smaller voltage, so it can't go any smaller than 0, so this must be 0. And I don't know, I should assign these maybe like this, 1K and 1K. So this is a divide by 2, so this voltage will always be half of this voltage. Okay, so we are outputting 0 because we've just been there for a while. So the op-amp sees 1 volt and 0 volts. It decides, this should be 5 volts now because 1 is bigger than 0. So this divide by 2 voltage divider now generates 2.5 volts. And the op-amp says, uh-oh, now 2.5 is bigger than 1, so I shouldn't output 5 anymore. Let me output minus 5 volts. Okay, minus 5 volts as the input to the voltage divider makes negative 2.5 volts. Now, 1 volt is bigger than minus 2.5 volts, so the op-amp says, I should output 5 volts now. So if we were to try to look at the V out versus time, we would think initially it was 0, and then it suddenly said, I should be at 5, and then, oh no, I should be at minus 5. I should be 5, I should be at minus 5. And it would alternate back and forth, probably very, very quickly. And that's one of the specifications of this op-amp is how fast can it do things like this. But the key is that it can't do it infinitely fast. So there is a little bit of slope to this line. So when the op-amp is outputting 0 volts, and we'll go back to a 0 volt input here, 1 volt bigger than 0 volts means that it will start to raise the output voltage from 0 towards 5, and as it's going there, it might actually decide not to go all the way to 5. It might not overshoot. So when would this op-amp stop overshooting? At what situation would the output just kind of sit at a voltage and stop moving? We're going to solve this, of course, with some solid math soon, but if we imagine that when this voltage is equal to this voltage, when they're both at 1, this voltage no longer has to change. Okay, we'll pick up on that soon, and we'll build a series of interesting op-amp circuits based on that relevation.